Well, welcome to this course, ENGI 428. And this whole course is CNC and PLC, programmable logic chips. And in this portion of the lecture material, we're going to be focusing on the programming logic chips as compared to the CNC material and some of the cybersecurity stuff that I mentioned in the last set of lectures. So I'm going to go ahead and just get into the specifics here. The first chapter that we are going to be talking about is giving an overview of what PLC, programmable logic controllers, are. And if some of you may have played with Arduino units, this will be something similar to that. The one distinction is this is more focused towards industrial applications. So you could say a little bit of a higher end and some specialized hardware like what we're seeing in this picture here. So let's go ahead and get into the details for this first chapter as we get an overview of what a PLC is all about. So this follows closely with the textbook. And so if you're following along and reading the textbook, you'll find that this is going to be a lot easier to see. So PLCs are widely used industrial control technology. It's most widely used industrial process control technology that's available. And this is contrast to the CNC when we're talking about manufacturing of parts. It's designed for machine process control, a computer built to operate in industrial environments, and equipped with input and output interfaces and a control programming language. Those are the things that what we're talking about here. It was initially developed to replace relay logic with its ever-increasing range of functions that includes timing, counting, calculating, comparing, and the processing of analog signals. And from the table of contents, you'll see that we're going to be going through those. So what does it do? It eliminates much of the hard wiring associated with conventional relay control circuits. And this is what you can see what the hard wiring would be. And this is what you would have instead by using the PLC control unit. So what does it do? It actually increases the reliability. Since all the logic is contained in the PLC's memory, there is no chance of making a logic wiring error. So that's encouraging. And plus you have the ability to fix things if something comes along. It has greater flexibility. It is easier to create and change a program in a PLC than to wire and rewire a circuit. It has lower cost. Generally, if an application has more than about half a dozen control relays, it will probably be less expensive to install a PLC. In terms of communication capability, it can communicate with other PLCs or computers, and so it can network, and that can be something that can be quite useful. It has faster response time. Machines that process thousands of items per second and objects that spend only a fraction of a second in front of a sensor require the PLC's quick response capability. So that's definitely a plus. It's easier to troubleshoot. To find and fix problems, users can display the control program on a monitor and watch it in real time as it executes. So you're not going to be able to get into the guts when you have a bunch of wires in that same way. It's easier to field test the devices. The PLC control panel has the ability to check field devices at a common point. So that's a first section. So here we're showing a PLC block diagram. You have the inputs and outputs. You have the programmer that actually is the one that makes all of this stuff that's then codified into the controller. And we'll see how this works. And of course, you need to have power to make this all function. So a PLC architecture, an open architecture design, there's two types, open and closed. An open architecture design allows a system to be connected easily to devices and programs made by other manufacturers. A system with a closed architecture is one whose design is proprietary, making it more difficult to connect to other systems. At least if you have standardized interface, you can have the implementation could either be open or closed architecture, or open or closed source, I should say. And if they even have the architecture, the interfaces are different, that's going to be a lot harder. There's fixed input and output. It comes in one package with no separate or removable units. And so here we're seeing the inputs. We can have an array of things that are there. This is reminiscent of what I've seen in a Raspberry Pi or an Arduino kit, if you've ever seen that. And so here we can be lining up these inputs, having the logic go between the inputs and the outputs. So keep that in mind. You can have this this type of configuration. You can have modular input and output is divided by compartments into which separate modules can be plugged. And so you can have a rack mounted where you have different pluggable devices that you can increase the capability, or have, if you need to have extra things that you're going to be controlling, you just add to it. We had a cartoon before, and this is a picture. The power supply provides DC power to all the modules that plug into the rack. For larger PLC systems, this power supply does not normally supply power to the field devices. The processor, the CPU, consists of a microprocessor for implementing the logic and controlling the communications among the modules. The processor requires memory for storing the results of the logical operations performed by the microprocessor, as well as the operating system and the PLC program. The PLC program is executed as part of a repetitive process referred to as a scan. Starting with the CPU, you read the status of all the inputs, and then this is the continuous repeating process that takes place. The input and output system forms the interface by which field devices are connected to the controller. Input devices such as push buttons, limit switches, and sensors are hardwired to the input module terminals. The input and output system forms the interface by which field devices are connected by the controller. Output devices such as motor starters, solenoid valves, and indicators lights are hardwired to the output module terminals. So a programming device is used to enter the desired program into the memory of the processor. And so here's you're getting that middle ground type of stuff of going from input to an output. A personal computer is the most commonly used programming device. The computer monitor is able to display more logic on the screen, thus simplifying the interpretation of the program. A program is a series of instructions that directs the PLC to execute actions. And this is what we're starting to see. We haven't talked about the syntax about this yet. And a relay ladder logic is a standard programming language, and it's based on electromagnetic relay controls. And that's what we're getting the chance to see with some of these cartoons that we're seeing, which forms of the schematic. So in terms of, let's move on here, the next section, the principle of operation. So for a mixer process control problem, a mixer motor is to be used to automatically stir the liquid in a vat when the temperature and pressure reaches pressure value, preset values. And this is what we're seeing here in this illustration. The manual operation of the motor is provided by means of a separate push button station. You can have a hardwired relay method for controlling of the monitor, control of the motor. The motor starter coil is energized when both the pressure and the temperature switches are closed, or when the manual push button is pressed. So you have a normal mode, and then you can have a manual bypass to make it do it. So in terms of the PLC method for control of a motor, the same input field device, pressure switch, temperature switch, and push button are used. Field devices are hardwired to the input module. For the PLC method for control monitor, the starter coil is hardwired to an input module, and the same output field, the monitor starter coil, is used. And we're seeing an illustration of that here in the figure. So to enter the ladder logic program, you enter the PLC ladder logic program into the memory of the CPU, similar to what you would do with an Arduino or a Raspberry Pi. The symbol represents instructions, and the numbers represent the instructions addresses. Each input and output device is given an address, which lets the PLC know where it is connected. Then running the program. For the program to operate, the controller is placed in the run mode. During each scan, the controller examines the status of the input devices, executes the user program, and changes output accordingly. The coil 0/1 is energized when the contacts I/1 and I/2 are closed, or when contact I3 is closed, when we talked about those two modes of operation. Either of these conditions provides a continuous logic path across a rung that includes the coil. For typical wiring required to implement the process controller scheme using a fixed PLC controller. This is how you would be using it. So the controller is fixed, but you can have various inputs and outputs that are then wired and making it a complete set.